started with in my last class I discussed about the small signal modeling of flyback converter. Okay, so here I am going to discuss about state phase averaging. So that portion I have most of the portion that I have covered. Okay, so if you want to classes are still required to complete this chapter. Okay, so I hope today and tomorrow means day after tomorrow the classes will be there, so I can cover that pending portion. So we can start our next section. Okay, next session section. So here we are just almost completing our state phase averaging with state phase averaging process. So you know that. Previous slides you can understand that different state phase averaging modeling or that processes for different converter like buck boost, then buck boost, then buck boost, now flyback. Okay, now we're going to take some another example. So what we can understand that from state phase averaging model. So that is a formal method. So state phase averaging method is a formal method for deriving the small signal AC equations. Okay, so small signal AC equations for a switching converter. So you are getting that switching equations. Okay, means AC switching equations. Okay, so simple thing. So there is not a big problem. Okay, so finally you have some set of equations for on condition, then off condition, then you are going to average state, and finally you will get some transfer function that is coming from your AC equations. Okay, so that's the basic motivations for state space averaging method. So okay, so then we are getting that equivalent modeling. So what is the next one? That equivalent modeling, equivalent to the modeling method. The previous sections means that previously I have discussed. So that previous sections we have discussed about the modeling. So we are getting that equivalent circuit, we are equivalent equation sets. Okay, use the state space matrix description for the linear circuit. So you know that switching equations, switching converters are highly non-linear. So now you are converting that non-linear equation to the linear equation. So definitely you will get some circuits, linear circuits. So you will get. Okay, so after getting that circuit, so you can say like the state phase matrix descriptions. So that circuit you will define in the form of matrix. Okay, that we can go for it. So often cited literature. So do you know that literatures mean different steps are there. So for the standard converter, so sometimes we are using different topologies of the other topologies, means other types of converter. Okay, so where we can implement the same method. Okay, so from this approach we can go for that. We can go for any of the generalized structure. Okay, so any of the generalized, it's a generalized structure. Okay, dedicated converter in different applications. Okay, so it is, you can see that it's a generalized approach. Okay, if the state equation of the converter can be written for each sub interval, okay, if each sub interval, then the small signal average model can always be derived. Okay, so small signal average signal, you can go for the derivations after getting that actual one, then only you can go for derivations. Okay, computer program exists which utilize the state phase averaging method. So that all the thing you can see that computing. So if you have that matrix, okay, so you have the parameters of the matrix, you know the specifications of that converter. So selection of that converter specification, another important issue. So which what will be your capacitor value, inductor value, then specifications of input voltage, output voltage, how to get that one. So basically you have to design the converter from your application oriented. Means if you want to design one means power supply for the computer, so that specification is different with when you are going for the design for that power supply of electric vehicle. So both of the cases the specification is different. Basically, you know, if you see that wattage, okay, wattage in power supply for computer is quite less, okay, compared to your power supply designing for your electric vehicle. Okay, basically that application oriented the power supply rating also been changed. Okay, So if the rating of the power supply is changed, definitely the topology of the converter has changed. Here I am going to discuss the very generalized topologies, very simple and generalized topologies. But in practical application, there are other types of topologies also been applicable, and you can see different new type of converter topologies. Okay, so that you need to, if you want to interested about the different topologies of the converter, you can download any of the white papers, okay, of different companies, means manufacturing companies like electric vehicle manufacturing companies. Okay, so where you can design, where you can download some white paper or the data sheet, so you can understand what type of specifications, what type of that parameter range they are using. Okay, so after getting the parameter range, so you have to select the solid state switches. Okay, so which application you are using your devices. Okay, so that also specified that rating of that voltage current of your system. Okay, so arbitrarily you are not able to select anything, select it as per oriented. Okay, so that's why it's a generalized structure, so you can define or you can derive your nonlinear practical converter in the mathematical form, and that mathematical form you can compute through your any of the software computing method. So you can get that linearized circuit modeling, and you can design the specific controller for your converter system. Okay, so that's the basic motivations for state phase averaging method. So state phase equations of a network. Okay, so now equations are there, so you get that canonical form for writing the differential equation of the system. So that how to design the, if you study that nonlinear control, that means one chapter is there like SFG. Okay, that means signal flow graph. So where you can see different form of that observer based control, then your different forms of there for that representation of that transfer function and graphical representation of your system. So that here you are using that canonical form for writing of the differential equations. Okay, if the system is linear, okay, so basically you are converting the nonlinear system to the linear mode. So if the system is linear, then the derivatives, okay, then the derivative of the state variables are expressed as a linear combination of the system independent of your input and state variable themselves. So if the system is linear, so then what happened, that your combination, linear combination of your system is independent of your input. That I told you in my some 2 days back in my the classes for last week. Okay, I told you na. So for that modeling, in the modeling I told you that there is no driving force, means D is 0. Okay, means changing of that V cap, V in cap means input voltage, you are making it AC portion of that input voltage, mean V cap in. Okay, V in cap. Okay, so V in lowercase suffix in and upper capping is there, you have considering it is 0. For what? That you are making that driving force. Okay, so that you are providing the driving force, means input driving force. That force is responsible for that independent inputs. Okay, means that V in. Okay, so that is forcefully you are making that AC portion of that input voltage is 0. So that may cause for that D of that equation is 0. If D is 0, then what happened? If D is 0, so definitely the system, that conversion of that system from nonlinear to linear, so it is makes sense, better sense, and it is quite helpful to that calculations. Okay, that's why we are making it, we are doing the changes. Okay, the physical state variables, okay, the physical state variables of the system are usually associated with the storage of that energy. Okay, so sometimes if you see the storage of the energy also changing the state of charge. Okay, so SOC, SOH. Okay, so how much charging a change, how much charge store is changing it in your storage, that also important features. Okay, for the typical converter circuit, the physical state variables, okay, the state variables are in the inductor current and the capacitor voltage. So you know the state variables for the any of the converter, switching converter circuit, that inductor current and inductor current and your capacitor voltage. Okay, so inductor currents means are in plural. Okay, voltage and current both are plural, means depends upon your energy storing element. So if two energy storing elements means are there, means in one inductor and one capacitor, so only two state variables. If two inductor, two capacitors, then it will be total four state variables, means two inductor currents and two capacitor voltage. Okay. Other typical physical state variables, that positions and the velocity of the motor shaft. Okay, so it's sometimes some dedicated application for machine drives. Okay, so that case, that position and the velocity of the motor shaft, that also been considered. Okay, for that physical state variables. At a given point in time, the values of the state variable depend on the previous history of the system rather than the present value of the simple inputs. Okay, so it's a state variable, so you know that minimal number of variables that can define the states of your system, means initial state, previous state, present state and future state. So three things you have to be in your calculations. Okay, so maybe your previous state is 0, okay, no problem, but in future state that should be considered. Okay, to solve the differential equations of the system, the initial value of the state variable must be specified. So definitely if you change that initial value, so definitely the trajectories of that eigenvalues, if you see that trajectory means path, the changing of the paths of that eigenvalue, it will be changed. It totally depends upon your initial values. Okay, if your initial value has changed, so system dynamics will be totally changed. Okay, so the selection of the initial value is also very selection of the selection of the initial value plays a significant role for the changing of the trajectories. Trajectory means locus. Okay, locus of what? Locus of roots. What type of roots? The roots of that converter is normally known as eigenvalue, not like converter, any of the dynamical system. Okay, that roots is your eigenvalues. Okay, so that is changing with your initial values. Okay, means locus of that path is most important. So if that locus is changing, so transient response, so changing of the locus, that have direct reflection to the transient of your system, means if it is very fast goes to the steady state point, then you can see that critically damped, but you can see that initial oscillation will be too high, means it will be more oscillating, that peak overshoot is high. Okay, and other kinds of features you can see. Okay, that's the point. Okay, so you have to be very careful about two selections of your initial points. Okay, here we are taking some examples. Okay, so some examples like state equation for a linear system in matrix form. So you know that formula, that k dx dt ax plus bu. So you know that y equal to output, it's your output equation in a canonical matrix form. So you know that specification. So x is your set of state variables. Okay, so xt, capital bold in x in lowercase but in bold in nature. So it is your state variables. Okay, and dx dt means what? It is the rate of change of state variables. It means so matrices are there. So differential equation of the matrix to know the state. Okay, that is responsible for to know the states. Okay, so state vector. So xt is your state vector, contain the inductor currents, capacitor voltages, etc. So x1t, x2t, generalized form. That's why they are not specified. Okay, so it is inductor current and capacitor voltage. That's why I have written like that way. Okay, so it is not specified like that manner. So input vector is ut, means this one. So it is your ut, input vector, in output. Both of the cases it is present. Okay, that input vector ut contain the independent sources such as Vg. Okay, the output vector is yt, contains the other dependent quantities to be computed. Okay, so yt contains means output vector such as IGT, so input current. Okay, the matrix K contain the values of the capacitor, inductor and the mutual inductance. So as per your applications, this is the generalized structure. K dx dt is a vector, contain the capacitor current and that inductor winding voltages. Okay, this quantity is as expressed as a linear combination. So what kinds of combination? It's a linear combination. Okay, linear combination of independent input and state variables. The matrix A, B, matrix A, B, C, matrix A, B, C, and E. Okay, so A, B, C, and E contain the constant of the. Okay, so all the values will be changing. A, B, C, E, all the values are changing as per the changing of the constant value, means parameters or system parameters. Okay, if you see that what is A is what? If you write the differential equations of that converter, means switching converter. So after writing all the differential equation, if you compare with this generalized equation, so you can see that A is a matrix that contains different parameters like your duty. Okay, duty of your system, means of your switching converter, means inductor values, means capital L, C, then load resistance. Okay, like the parameters is there in that A. So if any of the parameter has changed, okay, means any of the parameters has changed, then it has direct reflection to the converter dynamics. Okay, so is there any question?
Sir, the K matrix contains the inductor capacitor.
Huh, what happened?
The K matrix contains the inductor and capacitor.
Huh, K as well as A. Actually, what is K? K equal to, I am telling about A, not K. K equal to L dVc, sorry, C dVc dt. Okay, K equal to C sometimes, and A, K equal to L dIL dt. Okay, I am discussing about that A matrix, not K matrix. K is specified. Okay, that capacitor or inductor. Okay.
Okay, sir.
K is specified, means capacitor or inductance. Sometimes they are also using mutual, but I am telling about that A matrix. Okay, A matrix is the combinations of L. Okay, so that L, then D. Okay, sometimes load resistance R, C, all the components are there. Okay, that's why if you selection of the converter parameters also very important issues. Okay, so if we select the converter parameter in different manner, so sometimes the converter dynamics is totally changed. Okay, if I have some more class, okay, if I get some more class, so I can show you some of the slide based on that if I am changing that converter parameters, that you can see the dynamics, means phase portrait. Okay, the phase portrait of the system is changing. Okay, means if you see the limit cycle, okay, that the periodicity of the limit cycle is changing. Okay, limit cycle also some stable limit cycle as well as some unstable limit cycle. Okay, so I am considering about the stable limit cycle. I am not considering about the unstable limit cycle. Basically, that switching converter, every existing system are normally the example of a stable system. Okay, so here you can see one example. Okay, so some example you can see. Okay, all of you can draw it in your copy, so you can understand that input current is there, IN. So any of the equations here, you can see that one capacitor is there. Okay, that I current is flowing through the capacitor. Then IC1 current is flowing through the capacitor. Sorry, this is inductor. Okay, IT current is flowing through the inductor. Then capacitor 1. Okay, so it is C1. That V1 is that potential across your capacitor 1, and capacitor 2 is V2 is appear to the across to the capacitor 2. IC2 is your charge. IC1 is the charging current of your capacitor 1, and IC2 is the charging current of your capacitor 2. R2 and R3 both are there. Okay, it is your V out, plus minus is there. Okay, so you have to calculate the state vector. Okay, so state vector means you know that capacitor current and inductor current and capacitor voltage. These are the examples. So V1, V2 and I. Okay, so what is the K matrix? A simple thing. K matrix is, it is L1. So what is VL? VL equal to L di dt. Okay, and what is your C1? So in case of capacitor, so it is contain of C dVc dt. So C1 dVc1 dt, it is C2 dVc2 dt. So that's why you can see in K matrix is combination of capacitor and inductor. Okay, all are in diagonally present. So input vector. Okay, input vector means that input one, it is your IM. Okay, IN input current. Then choose the output vector. Output vector means output voltage and current. Okay, so output voltage V out and VIR1. So if IR1 is there, so output current is there. Okay. To write the state equation of the circuit, you must express the inductor voltage, capacitor current as a linear combination. Okay, linear combination of the element, and xt and ut are the vectors. Okay. So then circuit equation, also try to write it in your copy. So it's simple equations. Okay, IN is there. So you can find out that IC1, that charging current of capacitor 1. So find IC1 via node equations. Okay, so C1 equal to what? dV1 dt equal to I in t minus V1 by R minus IT. Okay, so simple thing, KVL we are using over here, the KVL. So why can calculate it, no problem. So in second one IC2, the same thing, same formulas you can apply over here and you will get that equations. Okay, then VL, okay, means it is your inductor voltage, VL1 equal to L di dt equal to V1 t minus V2 t. Okay, directly you are put over the and you can calculate it. Then equations in the matrix form. Okay, equation in the matrix form. So same equations are there. Okay, then you have that equations. Okay, now you are put it in matrix. So from this one. Okay, so from here you are making it matrix. Okay, so from here you can get it. So C1, C2, C3. So you can write down C1 dV1 t dt plus C2 into 0 plus L into 0. Okay, basically there is no combination. That's why C1 in the second row, that is C1 into 0 plus C2 dV2 dV2 t dt plus 0. Here C1 into 0 plus C2 into 0 plus L dit dt. Okay, like that way. So see, if you add both of them, so you will get this matrix C1 0 0 0 C2 0 0 L1. So it is your K matrix. Okay, and it is your state variable matrix. So state equations. Okay, that energy storing element. So dV1 t dt plus dV2 t dt dit dt. Okay, then it is your dxt dt. If you add all of them, so all at that point, so V1, okay, V1 V2 and V1 V2 and I. Okay, so inductor current I1 is your driving force, main driving force means it is input current one. So this is your input, so it is your V1 V2 I. So you can write in your copy, so you can understand that it is coming K dxt dt equal to A xt plus Vu. So directly this equation is coming here. Okay, so simple one. So if you try to simulate it, now you can do the simulation in MATLAB, no problem. So in matrix form you can get this one. Okay, then output. Okay, so output of that signal. So it is your equation from the matrix form. So output equal to what? Yt equal to V out IR1. So same thing, V out means what? You can see over there that voltage divider rule is using over there. V2 equal to your find output across R3. So V out equal to R V2, total voltage V2 into R3 whole divided by R3 plus R2. Simple formula. IR1 equal to what? IR1 equal to, it is coming V1 by R1. Directly it is coming this one. IR1 equal to V1 by R1. So that express of the element, that vector y is a linear combination of the element of x and u. Okay, the same thing, simple thing. Now we can express in matrix form that same equations. In the same equation, V out equal to what? V out equal to V2 R3 whole divided by R2 plus R3. So it is a V2. So directly you are getting that IR1, you are getting this one. Now you can make it a combination. So matrix form, in matrix form, what is that equation? So V out, Vi1. So you can write that. So combination of V1 plus V2. Here there is no coefficient of V1. So 0 into V1t. So it is coming 0. Okay. Then V2 component is there, R3 by R2 plus R3. R3 by R2 plus R3 plus there is no component of IT, inductor current component, this here the state variable, okay na? So you have to write that equation in the form of state variable, okay? That xt is common na? So from the formula what was written over there, so it was k dx dt plus axt plus but and y equal to cxt, so that 2 is the common, so it's your state variable plus e into ut, that input also been the same, okay? Input variable and state variable are same. So here what is your input? Input is in the form of input current, and k is, you know that one, yt means output is the form of v out and I r1, okay? So from here you can write that equation, means matrix. So there is no input current, so plus you can write 0 into I in T, okay? Same thing IR1, what is the expression of I1? There is some coefficient of V1, so it is coming 1 by R1, okay? Plus rest of the thing is rest of the state variable are 0, okay? Means multiplied with the 0 coefficient, mean V2 into 0 plus IT into 0. So that's why these two are the 0, 0, okay? So YT equal to CXT plus E into UT, okay? So you can see or you can understand that value, okay? Now the basic state phase averaging model, so what you can understand that given, so what is your given? A PWM converter operating in continuous conduction mode with two sub-intervals during the each switching period. So in this example, you can consider only two operating interval, means switch on condition, switch off condition, okay? But some of the specific converters are there. There is switch on configuration, switch off configuration, freewheeling configuration, define another mode also be there. So normally we are considering two modes of operation, but presently we are using fourth order boost converter, fourth order buck boost converter. So they are having 8 mode of operations, okay? So means lot of combination of different switches, okay? So some of the switches are on at that interval, some of the switches are off for the other interval. So it's a combinations of different switches, may be continuous conduction mode, may not be continuous conduction mode. But in this example we are considering some PWM switching converter, then they are operating in continuous conduction mode, okay, with having two sub intervals, okay, means on state and off state. So during switch on interval you have to write down the equations, okay? So when the switcher position 1, the converter reduces to the linear circuit can be described as follows. So that equations are there for A1, that A1, B1, C1, E1. So both are the coefficient for switch on conditions, and for during sub interval 2, that switches at the position in 2, the converter reduced to the another linear circuit that can be described by the following state equation: K dxt dt plus A2xt plus B2 ut and y equal to C2x2 plus E2 ut. Okay, so you can get that two set of equations. So similarly for equilibrium, for DC steady state equation, what you need to do for DC steady state means in average model you have to make that value 0, okay? So that difference steady state value, so derivative term will be 0, simple concept, okay? So that provide the natural frequency of the converter as well as the frequency of the variations of the converter inputs are much slower than the switching frequency. That I told you now, that switching, that frequency definitely, that sampling frequency will definitely much slower than your switching frequency, okay? At least 1/10, minimum 1/5 times up to 1/10 times, okay? The state phase average model that describes that equilibrium point. So here at steady state value we can get that equilibrium point, okay? So 0 equal to Ax plus Bu, then y equal to Cx plus E. Okay, where the average matrix are A equal to dA1 plus D dash A2, okay, and B equal to dB1 plus D dash B2, C equal to dC1 plus D dash C2, E equal to dE1 plus D dash E2, okay. Then equilibrium DC at DC component, so calculation of DC means steady state value calculations, okay, you need to go for it. So X equal to what? Equilibrium of DC steady state vector means equilibrium DC state vector, y equal to equilibrium of DC input vector, capital Y equal to equilibrium DC output vector, and D equal to capital equilibrium of DC duty cycle. Okay, so all are in the DC value. Okay, two things are there, one is capping point, another one is your DC. So how to calculate the steady state value or the DC value? So you can use this formula, so you can understand that values. Okay, then you can go for the solutions. Okay, so solution of your equilibrium average model. Okay, so here you can go for the equilibrium steady state average model for 0 equal to ax plus bu, so y equal to cx plus eu. So now you can equate by substitution. So from here you will get the value of x. So ax equal to bu, but here you can, so you can keep remember that all are in matrix. Okay, so directly, so what is that x equal to minus a inverse bu. Okay, I think you are able to understand. Then what is that value of y vector, means output vector in steady state, equal to, you can replace the value of x equal to minus a inverse bu into c. Okay, plus eu. So you can make a common of u. So u is common, so minus c a inverse b plus e within bracket complete multiplied with u. So I think you are able to understand that specifications. Okay. Now we can, that portion I think you have covered, means I think you have no doubt. Okay, so after that we can go for that small signal AC state phase average model. Okay, so that portion is also simple. Okay, so in small signal AC test state phase average model, here you can see it. So k dx dt. So here you can see that capping is there. Okay, so like your previous equation, so informal. Here I am discussing in the generalized form. Okay, the steady state one. Then we are going for the AC component. Okay, so capping is there. Okay, so axt, okay, plus but. Now that portion is there, D component is there. Okay, how it is coming? So you have on state equation and off state equation, then you are subtracting them. Okay, then you will get this one, get value, this value. Okay, then ut, then yt, that cxt plus eut plus within bracket c1 minus c2 into x in steady state value. You know that one, all the steady state value. Okay, so where you know that xt equal to small minus signal, so sorry, small signal AC perturbation in state vector. Okay, small signal AC perturbation. UT means definitely small signal perturbation in input vector. UT cap, XT cap, UT cap, then YT cap, the small signal AC perturbation in output vector. DT cap equal to what? Small signal AC perturbation in duty cycle. Okay, that we can understand over here. Okay, so if we can write the converter state equation during sub intervals 1 and 2, then we can always find the average DC and small signal AC models. Okay, so our agenda is to find out that DC value in steady state value and the small signal AC analysis value, means small signal model value. So now we can go for that state transition matrix. Okay, so how to get the state variables? Okay, you have that equations. Okay, that low frequency component of the inductor currents and the capacitor voltage of the model by averaging over the interval of length, time length is switching period is Ts. Hence we define the average of that state vectors. Okay, so you are doing that averaging the state vectors 1 by Ts is T2 T plus Ts. If it is starting from T instant, so definitely it will be continue up to T period, means T plus Ts period. Okay, so if it is starting from 0 seconds, so it will be 0 to 0 plus Ts, means 0 to Ts, but it is starting from T seconds, so it is coming T2 up to T plus Ts, means for the single period, time period. Okay, switching period and X tau. Okay, so that you know that low frequency component. Okay, the low frequency component of input and output vector are modeled in the similar manner. Okay, so you can model them input output vector. Okay, by averaging the inductor voltage and the capacitor current 1 octaves. Okay, so you have that average values of inductor voltage and capacitor current. So that portion is already discussed, so I am not recalculate the same thing. Okay, in my previous lecture it is already given how we are getting that D t into a1, that's d dash t a1. You are making it average now. So k d x t. So you are getting adding then dts plus d dash ts. Then you are averaging. Then it is directly coming k dxt. It is average over the cycle a ts and dt equal to dt a1 plus d dash t a2. It is your xt average with the time period ts plus dt v1 plus d dash t v2 and multiplied with your input vectors. Okay, input averaged vector over time period ts. Okay, so you know that state vector. Now you have to calculate the state vector for the first interval. Okay, the state vector means during sub interval 1. Okay, during sub interval 1 you have that vector k dx dt, that is your a1 xt plus b1 ut. Y equal to output vector yt equal to c1 xt plus e1 ut. So then what will be the elements of xt in the change in the slope? Okay, so you can get the same simple thing. So you can add them. Okay, you can add, you can get that value of dxt dt. So it is k inverse. Okay, k inverse that a1 xt plus b1 ut. Okay, small little assumptions. Okay, approximations. Now you can go for it. So element having of xt and ut do not change the significantly during the sub interval. Hence the slope essentially are equal to the. So you have to find out the slopes. Now you are making it average, that xt and ut over the time period ts. Okay, you have average both of them. If you are average both of them, so it is coming dxt dt equal to k inverse within bracket a1 xt average with ts plus b1 ut average with ts. Okay, that average condition you are obtained from there. So if you draw the slope, then you are getting that it is your initial state. Okay, that xt, so state vector during first interval. Okay, change of the state vector during first interval. So it's your average vector. Okay, so average value of that state variable, that k inverse a1 xt, yeah, it is average with ts plus b1, it is ut in ts. Okay, so it is your starting point in starting interval and it is running up to that portion. Okay, that it is your slope for a1 xt ts and this slope is coming that b1 ut. So it is a2. Okay, so k inverse a2 xt ts plus v2 ut ts, that another slope is there. Okay, so you can see it is your average line, it having some slope up to dts you are calculating. Okay, total time period you are not calculating, only dts you are calculating. Okay, so what you can write, the net change of state vector over the first interval, over the first sub interval. Okay, so it is coming x dts means final value. Okay, equal to x0. X0 means your initial value. Okay, plus time interval, so it is your interval time into slope. Okay, so that is coming y equal to mx plus c. So c is your x0. So m, what is your m? M is k inverse a1 xt over the time period ts plus b1 ut over the time period ts. Okay, k, that is your slope, and m, this is your m, x is dts. Okay, that is coming. So then second interval, second sub interval, you have to calculate the same thing. So it is coming. So what was that value for the constant slope? It is dxt dt equal to k inverse within bracket a2 xt. Okay, within bracket a2 xt plus b2 into ut ts. Okay, so then what will be the second sub interval, the equations? So it is final one, here you have written the final one, so it is coming x dts. Okay, so it is your final one, and that final one is the initial one of your off time interval. So it is your initial one, that off time interval. So x dts, that is initial value, again that y equal to mx plus c. Okay, so it is c, that means it was completed with x dts. Okay, that value we can replace. So total x dts means that x0 plus dts k inverse a1 xt plus b1 ut what the TS period, so you can replace that value directly over here. Okay, from the previous equation you can directly put that value, and XTS is your final values of the state variables over the after completing that your switching time period. And that is what is your interval length. Interval length is d dash ts. Okay, it also multiplied with that slope. The slope you can calculate from your off state equations that you can directly put over here. Now you can replace that value. Okay, that you have that value, a dts x dts equal to x0 plus dts k inverse a1 xts plus b1 uts. So net change of state vector, okay, over one switching period, and it is your that equation 1 and equation 2, xts equal to x dts plus d dash ts plus k inverse a2 xt within the time period ts plus b2 u2 within the time period ts. Okay, so now you can eliminate both of them, so directly place put this one. So after eliminating xt to express of xt is directly term to the x0, so it is coming that one, xts equal to x0, xts equals to x0 plus dts k inverse a1 xts b1 uts, so d dash ts k inverse a2 xts plus b2 uts. So collect the terms. Okay, so finally you will get that expressions. Okay, so you can make a common that portion, so that xt average with ts and ut average with ts. So this term you can make a common. Okay, these terms you can make common, these two are the common, sorry, these two you are making common and these two are making common. Finally you will get that equations. Okay, so that equation you are getting, so you are making common xt. Okay, and tsk inverse you are making it common, it is coming dta1 plus d dash ta2. Okay, so here you are also getting tsk inverse, then dtv1 plus d dash tv2. Okay, so then I think all of you are understand. If you have any confusion you can ask me, so again I can re-discuss if you have any kinds of difficulties. Okay, now we can add both of the slope in your system. Okay, so both of the slope means you can draw that one, so it is your x0 and xt. Okay, so it is initial, so first last step of your mode 1 condition means sub interval 1 condition, it is for the sub interval, then this portion is sub interval 2. Okay, and you are getting that, sorry, average value, and this the slope of your on time equation, and this the slope of your off time equation with the average value. Finally you will get the state equation that xt dts. Okay, so that point is simple. Okay, xtts simple. So using Euler approximation, okay, so you can make it that formula, so xts minus x0 whole divided by ts to find out that average. So it's a differentiation na? So dxt over the ts means what? Derivative means you are making that subtracting, so dt means total time period ts, and difference between that xts minus x0. So you can replace that value, you have that value, so you can replace the xts from your previous equation, that xts. Okay, this one you can replace it. Okay, if you replace it, so x0 are cancel each other, only ts k inverse, these two are there, so ts is common both of the equation, and derivative divided by ts, so ts cancelled. So finally you will get that value of derivative 1, you are getting that k dxt dt. So k inverse is there, so you can make it left side to right side, sorry, right side to left side. So k is there, dxt dt equals to dt a1 plus d dash a2. You are multiplying with xt to tx, and dt v1 and d dash v2 multiplied with ut ts. Okay, I think you are able to understand the simple thing, that total portion you should do in your class work copy. So after completing this chapter you have to submit it. Okay, so day to day you have to make it updated. Okay, then we can go for that output vector. So previously input vector, input portion I have completed, means that state vector I have completed. So output equation, the same thing they are using, that yt over the ts. Okay, they need to calculate. Okay, so it is a c1 xts plus e1 ut ts. Okay, similarly removing the switching harmonics and averaging the period, so c2 xt ts. So that is rechecking, you should recheck in your home, okay, and do that derive these details calculations. Okay, only there is output is written over here, okay, but rest of the step you have to do it in your home. Okay, yt average with the period means total time period ts, it is dt into c1 xt. So finally they have written that final equation like that way. So c1 xt then dt d dash t, it is c2 xt plus e2 yt. So you are making it average, so make it common. Okay, so which portion is common? So state variable you are making common both of them. So dt c1 plus d dash t c2, and it is again that ut average with ts period we are making it common, so dt e1 plus d dash t e2 we are making it common. Then average equation, that quasi operating quotient operating point, that means linear point, that is we are going to find out the average or non-linear state equations. Finally we will get that equations. Okay, that state equations dta1, that formula directly they are taking that formulas from here. Okay, from here they are taking the equations and put here. Okay, that directly they are putting here, and similarly that output equation, from this output equation they are written over here. Okay, that value of yt equal to dt c1 plus d dash t c2. So converter operates in equilibrium. Okay, so you know that it's operating in equilibrium when the derivative of all, elements of xt ts at 0. So they are making it 0. So that portion is 0. So if you are making it 0, then what happen? So that total thing will be 0. So that portion will be 0. So that quotient operating point is the solution of 0 equal to x plus bu plus then y equal to cx plus eu. Okay, that x equal to equilibrium at state vector, y equal to equilibrium of input vector, y equal to equilibrium of output vector, d equal to equilibrium of duty cycle. So we'll get all those values a, b, c and e. Okay, then you can go for that averaging, then perturbations. You can use that perturbation method. Okay, so average state equations, that perturbation and linearizations, that is your like your previous one, so I am not going to discuss that point wise. So you can get from there, the slide will be available with you, so you can do the solution. That portion I have already completed. Okay, that portion I have already discussed. Okay, that's why I am directly showing you the answer. So perturbation you are using, that one is steady state value, another one is your cap value. Okay, you know that constraint, all those things. So perturbations are there, and finally that average state equation, that the perturbation and the linearizations. Okay, so then you have that equations, then DC component, first order AC component, same DC plus first order AC component and DC component. So perturbation, you are doing that perturbation, second order nonlinear item, and first order AC terms, first order AC terms, and second order nonlinear terms. Okay, then linearizations of that small signal equations. So finally we will get that equation x k dx dt equal to x plus bu plus da1 a2. So from this one, okay, you will get that value. So nonlinear portions will be 0, make it is 0. Okay, you have make it is 0. Same thing, that nonlinear portion you are make it is 0, but rest of the portions, okay, that one, okay, that one and this one. So perturbations, from here you are getting that AC component yt equal to this value plus this one. Okay, so from where it is coming. Okay, so I think you are able to understand. So from here you are getting that second order, or the nonlinear terms are small, then you are neglecting. Okay, as I'm saying, satisfied. So left one you are getting that one. This is your desired result. Okay, so I think you are all of you able to understand, and you can cross check it to your home and up to date your class note, because I just completed my module within few days. Okay, within next day. Okay, I have completed this module. Again, I will ask for that submission of this class note of this module. Okay, so you can follow the book of Erickson. Okay, that's a very good book that I am following. Okay, so if you have any doubt, you can ask me. So today I will close my session. from this point. So next class I'll discuss about the equations, means small signal equations for boost converter and buck boost converter. For that I am not considering any ESR value, without considering any ESR value. Okay, in my last discussion I have considered the ESR value and we just show you that equation. So in my next class I'll discuss about the equations of boost converter, buck boost converter by using this method without having ESR value, means equivalent series resistance components. Okay, so if you have any doubt you can ask me. So today I have stopped my sessions actually. If you have any query, so you can ask me. Okay, I think I don't have any query, so okay, so I just stop my session.